we turn our attention to chapter 16 and even more equilibria problems. And we'll start with just a little bit of review, essentially, although you could think of it as being something that we're going to work on too. We're reminded that in a Lewis acid and Lewis base, or a Bronsted-Lowry acid base, that we're talking about the idea of donating protons in the case of the Bronsted-Lowry and donating electrons in the case of a Lewis acid base situation. So the question is, out of these, which of the particles could donate a proton? Well, the question really is, do you have an H that might be able to get loose? This first one, well, there is an H, but this already is an OH minus. Very difficult for it to get away. But in the right circumstances, yes, it could be pulled away as a proton. Very unlikely, but it could happen. Meanwhile, though, because you have this idea of the lone pairs around the rest of the oxygen, it could clearly accept protons very easily. It will welcome them because of the minus sign here. If a proton comes along with a positive charge, it's going to love to come and join in here and make nice, stable water. This is NH3, ammonia. NH3, if you stop to think about what its Lewis structure is, it has a lone pair. So it can clearly accept a proton. It's got H's all around it, so it could donate a proton. It's not likely to, but it could. Much easier than this could because it's a neutral. Here we have ammonium ion. Now this can definitely donate a proton because it's already got a positive charge. So letting one of these go, carrying a positive charge, would make it back into this. So yes, it would love to donate a proton. It absolutely cannot accept one though. If you'll remember what nitrogen is all about, it's in the second period, so it can't break the octet rule. It's already got full octet around it because of having 4 of these hydrogens around it. So it can definitely not accept a proton. Here we have the water, which we were talking about. If this accepted, if the OH minus accepted a proton, it would turn it into water. Well, then if this water let go of an H plus, it would turn into the OH minus. But, you know, it also does have 2 lone pairs still on the oxygen atom, so it can accept a proton as well. That helps highlight how a lot of things end up being in a position where they could act as either an acid or a base, depending on the rest of what's in the solution with it. So we've already talked about these lone pairs. This has lone pairs, this has 1 lone pair, this has 2 lone pairs. None. And then to think of it in the way that Lewis does, instead of the way Bronsted-Lowry does, is to say, gosh, why do we keep talking about protons when we know that electrons are what make the bonds? That was what Lewis did to make a big difference in the definitions of acids and bases. And once he did that, it got us away from having to do everything in aqueous solution, because lots of things can donate or accept a pair of electrons without having anything to do with water. So when you look and say, what can donate a lone pair of electrons? Well, all 3 of these can. This doesn't have any lone pairs, so it cannot.